So in this video, we're going to tackle probably the most important concept in this whole course, which is the normal distribution. And the reason I say it's the most important concept is because the basis of almost all statistics is that data is normally distributed. So it's really important to understand, well, what does that mean by normally distributed, and what does it bias? And so we're going to look at all of that in this lesson, and then in the next lesson as well. So imagine that we have some sample data. Sample of 100 employees appears below. You've got the employee ID, first name, last name, and their salary. And here they've been sorted. And they're basically sorted to match this histogram. So you can see, salaries between 26,000 and 34,000 are this light color here, 34,000 to 42,000 at this slightly darker blue, and then slightly darker blue for the next group, and then we start the greens starting darker and getting lighter all the way down through this histogram. So the first exercise we're going to do is just go ahead and recreate this histogram. We won't create it with all the pretty colors unless you want to, but we'll just create the histogram. And so the way we're going to do that is to highlight this column, and then we'll go to the Insert menu, pick Recommended Charts, and look for the one that looks like a histogram, which is this one. And then drag it back up to where we want it. Sometimes that takes a little while. You can also cut it from where it was and paste it up where you want it, depending on how you want to move it. All right, now this histogram looks a little bit different. This one has 6 bars, this one has 7, and we can change them to match. So on a Mac, that would be clicking on the bars. On Windows, it's going to be right-clicking on the axis. But at any rate, then you go to the format, here, the axis of the data series. And then for the number of bins, right now it's set to auto, but we're actually going to force it to 6. And just so the pictures look the same. And you don't have to worry about making the colors match. If it really bothers you, then what you can do is click on one of them, right click, and if you format the data point and then the fill, you can actually play around with that color. But that's up to you. Okay, we're not even going to worry necessarily about the bins being an exact match, but it does look like they did in my case. All right, now this sort of kind of looks like this, and that's the key to statistics. We take things which sort of kind of look like normal, and we just go ahead and say, well, they are normal. In other words, they're close enough that we can call them normal. And the reason that we want that is because then all the rules that apply to normal distributions can apply to our distribution. So we're going to see if that's true. One of the rules that does apply, or properties for normal distribution, is something called the empirical rule. And the empirical rule simply states that if your data is normally distributed, so this is the mean here, that and that sigma means standard deviation. It means that if you go 1 standard deviation to the left of the mean and 1 standard deviation to the right of the mean, that between those two boundaries you'll have 68% of your values. If you go 2 standard deviations, you'll get 95% of your values, and if you go 3 standard deviations, you get 99.7, which is basically everybody, or almost everybody. So this turns out to be really useful, especially when we're doing hypothesis testing later on, to see if something was likely to happen. If something's way out here in the tail, then it was probably unlikely that it would have happened by chance. Okay, so if our sample distribution is close to normal, the empirical rule should hold. So let's see if this is true. So let's look at the actual average for our data. And let's look at the actual standard deviation for our data. And ours is a .s because it's sample, not population data. All right, and then the mean, now we'll fill out this little thing to see if we can match these boundaries here. So our mean is 49,000, And if we subtract, we go equals that minus 1 standard deviation, we get that number. And over here, if we go equals the mean plus 1 standard deviation, we have that number as a boundary. And then if we click here and we say, well, that's equal to the mean minus 2 times the standard deviation, and then over here, this is equal to the mean plus 2 times the standard deviation. All right, so these are our boundaries. And now let's count how many people fall in these boundaries. So theoretically, right, theoretically, 68% of our entries should fall plus or minus 1 standard deviation from the mean. And we can actually count the entries and see if that's true. So we'll do count ifs. The criteria range is this. And the first criteria is that we are greater than the lower bound. And then we run the same group of criteria range, same criteria range again. And this time we look to see if that's less than or equal to the upper bound here. And lo and behold, we get 68. Since there were 100 entries here, that means 68% of these entries followed this empirical rule, which kind of sort of helps lend support to this data actually being normally distributed, even though it doesn't look like a perfect bell curve in the same way that this one does. Okay, and then we can test again for 2 standard deviations, right, which we would expect to be 95%, 95.45% of all our observations. Let's see if that's true. So that is equal to count ifs, criteria range, and then well, actually, why don't I just copy that formula and then edit it? That might be easier. Let's try. Let's just move these guys to here and here. And hope and pray that that got it. I don't think it did, because unfortunately I didn't lock the range the first time, so I'm going to have to fix that. So that's close. But this should have been E8, T107. So let's get this range again. If I'd locked it, which hopefully you did, then you wouldn't have this issue. There we go. And it's 96. So is 96 95.45? No, but it's awfully close, right? So the empirical rule seems to hold. This data, which is not perfectly normal, is behaving as though it's normal, at least as far as following the empirical rule. So that's really cool. This empirical rule is so important that we have a couple more exercises on it. So here's another normal distribution. Here's another empirical rule. So here's the mean at 100. And this is a cell phone provider has determined that its average salesperson sells 100 smartphones per quarter with a standard deviation of 15. And so that's all you need to know about the distribution, what its mean is, and basically how wide it is, right? Because the standard deviation is effectively how wide, in other words, how spread out the values are, what their average distance from the mean is as you go east-west. And so what percentage of employees sell between 85 and 115? Well, here's 85 at 1 standard deviation. Here's 115, right? So we know that between that and that is going to be 68% by the empirical rule. So just type 68. What percentage sell between 70 and 130? Well, that's going to be the 68 plus the 26, 27 here, right? So that's going to be 95. And between 55 and 145, right, that's almost everybody. So we add another 4%, that 2 plus that 2. So it's 99. And what number is the mode? The mode is always the same as the mean, median, and mode in a normal distribution, always the same, right in the middle, which is the mean value, so that's 100. What's the likelihood a randomly selected employee will sell 70 or more? So what's the likelihood you'll be here or more? Well, that's kind of hard to figure out because you have to add all these up. It'd be a lot easier to figure out how much was left in the tail, which is the 2% plus the 0.5%. So that's 2.5%. So basically just take 1, subtract 2.5, and we'll have it at 97.5%. What sales number is the 50th percentile, which is also the middle, the balancing point, the median, because remember, mean, median, and mode are the same, so that's 100. What percentage of employees sell between 70 and 85? So between here and here, that's 13.5. What percentage of employees sell between 100 and 130? So that's between here and here. So that's 34 plus 13.5 is 47.5. And what sales number is at the 16th percentile? So 16th, there's 13.5, 15.5, 16, so it would be right here, 85. All right, so that's the empirical rule. That's kind of, if you want to do sort of a quick and dirty and everything falls right on the boundaries, but unfortunately life doesn't always work out that way. And sometimes you need the number, well, what's the number in between these different things? Like in other words, when we have to be very precise about where we are on this curve and we don't fall right on a boundary, how do we calculate things? And that's what the next series of tabs is about. So here we have a situation where Katie sells in the East Division where the average sale is 30,000 and the average distance from the mean is 5,000. Distance from mean is the same as standard deviation. Her sales are 40,000. What's her percentile? So let's first frame the problem. And in this case, we're looking for the probability below x because that's the percentile. What's everything to the left of. Pick the function. The function we're going to use is norm.dist because norm.dist gives us probability. We have all this information. We have x mean and the standard deviation, but we need probability. The case is one-tailed to the left, and this is going to become very obvious as the problem develops. You'll see what I mean. And the mean or average is 30,000, and the standard deviation is 5,000, and her sales were 40,000. And so the question is, what's the probability of her sales? Well, we can already see it here. These graphs build automatically in the background as you complete this up here, which is kind of cool. And we can see Katie here. Here's Katie at 40,000. Her z-score, which is 2.0, which means she's 2 standard deviations above the mean. Right. So for this one, we actually could have used the empirical rule because it falls right on a standard deviation border. And here's the mean of 30,000. But if we come over here, we can actually see visually what the problem is asking for, which is what percentage of people are to the left of Katie, right? And that's 97.7% are to the left of Katie. See the little arrows to the left of, and there's the z-score of 2.0, and then that's her absolute number, the 40,000. So this visually shows what the problem is asking for. But let's see if we can calculate, how did we get that 97.7? And we can't just type it in here. We'll get an error message because it insists on a formula. And the formula that we use is norm.dist x mean standard deviation, and then we put true at the end, because we do want the cumulative to the left of her, 97.7. What's her z-score? Well, there's 2 ways that you can compute a z-score. You can either do it off the probability, or you can do it the way we typically do it, is we do x minus the mean divided by the standard deviation. So that's how we get the 2.0. What do z-scores measure? It's the average distance from the mean in the standard deviations. And what is a standard deviation? It's the average distance, just the average distance from the mean. Okay. You can ignore these controls will appear down here. These are the controls that actually paint the graphs, and they're simply linked to the problem. You're better off not messing with these because they'll mess up the graph. These update automatically. Okay, let's go over here. Josh's sales rank. Josh sells in the East Division where the average sales 35,000, average distance from me is 10,000, his sales are 40,000. What percent of sales people are above him? So let's frame the problem, which is find the probability above x, right? We want to know the percent of people above him. Pick the function. It's going to be norm.dist again, because we're after a probability. The case is going to be to the right, though, not the left, like it was before. And the mean is 35,000. Standard deviation is 10,000. X is 40,000. And now probability of x equals norm.dist x mean. Oops, I picked the wrong thing for mean. Mean standard deviation true. Made a mistake. Value too high. Why is it too high? Okay, so the reason it's too high is that we want to the right of. So this gave us a percentage, but norm.dist gives the percentage to the left. In other words, in this diagram, it would be all the white area in here. But we actually want the red area. Well, all the areas together add up to 1. So to get the red area off the white area, all we do is at the beginning of all this, put 1 minus. So we're going to take 1 minus the probability we just calculated. Then we get our 30.9%, which does match what's here on the graph. How many standard deviations above the mean is Josh? Right, so that's going to be his z-score. Remember, that's equal to x minus the mean divided by the standard deviation. And that's also reflected here, the 0.5 z-score. And what is a standard deviation? It's the average distance from the mean. So this is kind of cool. Here's Josh, and about 30.9% of all the employees are above Josh, which is what the question was asking. All right, now we're going to get into some more interesting examples, like strongest performer. So Katie sells in the East Division where sales are distributed. When you see this N, 30,000, 5,000, it means N stands for normally distributed, mean of 30,000, standard deviation of 5,000. Her sales beat the average by 7,000. Josh works in the West. Her sales are distributed 35,000, 10,000. His sales are 40,000. Find and compare the percentiles. In other words, who's the better salesperson? Because they're selling in districts that have different means and different standard deviations. So the question isn't how good you are. It's against the person in the other division. It's how good are you performing in your division? How good are they performing in their division? And now let's compare you two. So this is critical for doing comparisons, and this is going to be true throughout so many venues, especially in business, including like comparing stock performance, etc. But anyway, let's frame the problem. So we're going to look at the probability below x, because we're effectively saying, what percentile is each one in? Pick the function. Again, it's norm.dist. You're going to see that a lot. And, oops, it's one-tailed left in both cases. And the mean is going to be 30,000 for Katie, 35,000 for Josh. Standard deviation is 5,000 for Katie, and 7,000 for Josh, and x is 37,000 for Katie, Somehow I made a mistake on Josh. Let me see. Oh, sorry, his sales are distributed 10,000 normally. And then X is 40,000 for Josh. All right, now, the graph has already solved it. We're going to have to solve it in a second, but we can get a feel for what's going on, and this is really amazing. So here's Katie. Here's Katie's division, this red line, the mean of 30,000. There's Katie, so she's above the mean. Right, how far above the mean? Well, she's 1.4, the z-score is 1.4 standard deviations above the mean. That turns out to be a more meaningful number to compare the two than to say that she's 7,000 above the mean, because these are two different scales, right? So here's Josh at 35,000. He's selling 40,000. So he's selling, in absolute terms, he's selling more than Katie, because she only sells 37,000. But he's only 0.5 standard deviations above the mean. Now, it's hard to see it here because they're on different graphs that are sort of on different scales. But if we put the two together, just based upon the z-score, right, we can see clearly that Katie's ahead of Josh. It's harder to see it from over here, but it's really clear to see it here. So what is this plotting? This is plotting everybody according to their standard deviation, right? And now you can see Katie's in the 91st, almost 92nd percentile, and Josh is just in the 69th percentile. So she's clearly the better performer relative to her peers in her division. But let's go ahead and finish off how we actually calculate this. So it's norm.dist X mean standard deviation true. There's Katie. There's Josh. And the z-scores equals X minus mean division. And so who performed better relative to their division's average? It's Katie, because she's in a higher percentile. Now we also have some multiple choice questions down here. How many standard deviations is Josh away from the mean? Well, that's his z-score, so he's 0.5. How many standard deviations is Katie from the mean? Well, that's her z-score, which is 1.4. Could you have picked Katie as the best performer, even from this graph? Even if you didn't see this one where she clearly is the best, could you have gotten it from here? And the answer is yes, by looking at her z-score. She's got a higher z-score, so she's further away from the mean in a positive direction. So that's going to be A. And now the answer block all turns green, which means we got them all right. All right, this next one, top scores. We've got in Professor Jen's class. This is kind of a neat one too. Like, in which class can you get an A in? This is kind of neat. On Jen's class grades, just really normally with a mean of 70 and a standard deviation of 15. Alex's class grades should be normally a mean of 84 and standard deviation of 5. If you want to achieve an A grade, which is set at 93 in both classes, compare the difficulty of obtaining in each class, considering the grade distributions in which professor's classes is easier to obtain an A grade. So this is kind of neat. So this is going to be find the probability above X, right? In other words, what's the probability that a given class member is above the 93? Pick the function. It's going to be norm.dist. Professor Jen is going to be one tail right. Alex also one tail right. The mean in Alex's class, 70. In Jen's class, it's 84. And the standard deviation, Alex, 15, 5. And in both cases, we want to get a 93. So what's the probability that we're going to end up with 93 in both cases? That's what we're trying to compute. So we said it already, it was going to be norm.dist. but we're going right side, so it's got to be the 1 minus. So 1 minus, didn't want that. I start with an equal sign, equals 1 minus norm dot dist x mean standard deviation true. Copy that. And the z-score is equal to x minus the mean divided by standard deviation equals x minus the mean divided by the standard deviation. Okay. So now we can look at it on the graph. So here's Jen for a 93. Here's Alex for a 93. You can see that the distributions look really different. So Jen's class has a much bigger standard deviation. The grades are spread out more. And do you see the effect that has in the tail over here? It means that she has more area here in the right-hand tail than Professor Alex. And you can see that over here, right? When we actually, it's maybe a little harder to see over here, but really obvious over here. Here's Alex's class, and here's Jen's class. So you have a higher probability, 6.3%, of getting an A in Jen's class than you would in Alex's class, which is 3.6%. So you can see that when you've got this situation, you're trying to do comparisons, it's awfully nice to put the comparisons on the same graph, but to get them on the same scale, we have to make the x-axis of this graph the actual z-scores, whereas over here the x-axis was actually the raw numbers. So in which scenario are you most likely to earn an A in Jen's class? Because there's a higher probability of a grade above 93. All right, now we have some multiple choice questions. Which step is correct when using norm dot inverse to find a grade x for a given probability above x? So this is if we were going to work backwards, right? I mean, which is different than we did in this problem. But since it's above, we got to do the whole 1 minus. So subtract the probability from 1 and then use this in norm dot inverse if we were working backwards. If you know that 5% of the students score above a certain grade, which helps you find that grade, again, that would be norm dot inverse. That's if we were working backwards. We weren't in this problem, but if we were. And if you need to score 93 to get an A, what's the approximate z-score for this grade in Professor Jen's class? And that's going to be the z of the 153. And the answer black turns green, which means we got it all right. All right, what about debt comparison? See, these comparison problems are fun because it allows you to compare people that are on different scales and put them on the same scale by boiling everything down to a standardized measure, which is the z-score. All right, so first let's look here. Steph's credit card debt is normally distributed mean of 5,000, standard deviation of 1,000. Her debt is $1,500 below the mean, Aiden's student loan debt. So now you're comparing credit card debt to student loan debt, which seems like a strange comparison, and the numbers are very different in terms of absolute scale because student loan debt is obviously much bigger, or usually much bigger. But we can still do the comparison of everyone relative to their own debt, right? Debt class. So who's in the better position? So it's probability below x, norm dot dist. Case is one tail left for both. The mu in this case, 5,000. this case, it's 30,000. So very different means. Standard deviation is 1,000. And here it's 5,000. And then X, she's 1,500 below average, so she's at 3,500. And Aiden is 2,000 below average, so that puts him at 28,000. All right. So let's look at the probability. So that equals norm dot dist x minus the mean. Oh, sorry. That was weird. Sorry, norm dot dist x mean standard deviation true. That's going to be the same over here. And then the z-score is equal to x minus the mean divided by standard deviation. Who's in a better position? Well, you can see Steph's in a lower percentile, so her dad's in a lower percentile. Let's look at it in pictures. So here is, remember, really different scales, right? So here's Aiden. There's his 30,000, and he's below that, but with just a z-score negative 0.4. Here's Steph. With her credit card debt, mean is 5,000. She's at 3,500. But at 3,500, she's way below that because the standard deviation is so small. All the observations are clustered close together. And you can see that even better here. There's Aiden in the 34th percentile, and here's Steph in the 6.7 percentile. So if you need to find the debt amount where only 10% of the people have less debt, what probability value should you use in the norm dot inverse function? Going to be C. If you want to determine the probability that someone has a lower debt than a given amount, which function should you use? Norm dot dist. And what does a negative z-score indicate about a person's debt relative to the average? They're below the average. All right, we got all this. And now we've got one which is going to, we've been hinting at working the other way, but now we actually are going to work the other way. We're going to be given the probability, and we're going to have to find the value of x. So frame the problem. So this is Daniel is studying the heights of rare tree species of the Amazon, which are normally distributed. Mean of 100 and standard deviation of 15. He wants to find a tree in the top 1%. How high does the tree need to be to qualify? So that's going to be find x given the probability above, because we're trying to find x is at the 1%. Pick the function, and this time it's going to be norm dot inverse. And the case is one-tailed right. And mu is 100. Standard deviation is 15. X is what we're looking for, but we do have P of X, which is going to be the 1%. All right, so let's try to calculate this. So that's going to be equal to norm dot INV. We have to put in the 1 minus the probability since we're going to the right. 1 minus the 1% here. And then the mean and standard deviation. So that then filled in the graph. So there's the mean, which is 100. The rare tree that he would find in the top 1% would be 134.9 feet tall, 2.33 standard deviations above the mean, right? And there it is with the probability, the 1% probability. All right, so where does Daniel's tree height fall relative to the average? It's in the top 1%, because that's what the problem specified. All right, how does Daniel's tree height compare to the mean? Like, it's way above the mean, so that's going to be C. And what does the z-score 2.33 indicate? That he's 2.33 standard deviations of the mean, and his percentile all right, so we got to pick one. He's in the 99th percentile because it's the top 1%. And we're all set. So, when you're looking at these problems, we will try whenever possible to give you a visual. Those visuals are the key to your understanding of what's going on. And remember, these visuals, which look like normal distributions, all tie back to that original histogram that you saw earlier. In fact, we're kind of trying to show it with these little red lines here. This is just this normal distribution is just a really, really fine histogram. You know, if we had sort of almost an infinite number or a very big number, let's say, of observations, we expect it to smooth out into a normal distribution. And we'll talk more about what that means in the next video.